This video is going to be about the not so straightforward world of propellants used for firing projectiles from firearms and non-firearm items, like, potato cannons and shooting, anvils and whatever else you're into. This is being done mostly as an example of conversions, problems, and it's an exercise in futility doing this. Now we're going to be using a set of definitions. One of the definitions is for a measurement that many of you may not hear of, and it's called the grain. This is based on 1/7,000th of a American pound. That's a joke about Britain having their own gallon version. Anyway, but 1 pound sterling, no, for 1 pound of weight, if you divide it up 7,000 times exactly, you end up with a grain of barley's mass. Yeah, that's what it's based on. I thought it was based on a grain of rice, but it's actually a grain of barley. It was corrected for me. So, yes, if you take 7,000 grain, yeah, it's consistent enough that was used as a measurement method. Let's move on. People used to use pennies for scales. Okay, go on. Now, we're going to be also using black powder with the following definition. This is the one found in most physics and science papers because if you're doing science experiments, you want things consistent, so they would just make this bog standard 75% potash or potassium nitrate, 15% charcoal, and 10% sulfur. The reason for that is that's actually pretty close to what everybody made, and gunpowder is quote-unquote forgiving in that there's not many modifications you can do to it that will make it behave differently. Warning, with black powder in a firearm, it needs to be packed tight in a space with very little gap or no airspace around it. Otherwise, this curve that it creates as it goes up and then it slopes off as it pushes things out of a barrel will turn into a sharp spike. Coincidentally, smokeless powder is defined as powders that do not behave like gunpowders, because they're not black powder, and they do have that spike. So if you get a gun and it says black powder only, unless it's something really big bore like a 12 gauge, it probably cannot tolerate smokeless powder. Probably. Shotguns are weird in that they have such a huge bore that the pressure buildup is almost exclusively done inside of the cartridge first, and then in the barrel. Even though there should be some hoop stress math for it that says that you're doing something dangerous, you really aren't. And that's something people don't want to hear. Unless it's a black powder firearm. Then suddenly, yes, you have to have the thing over-designed to the level they can handle smokeless powder under the worst possible conditions before you do any experiments. That's why YouTube and Google have rules about not showing people how to do this or not doing experiments, because this is considered dangerous activity. This is just math. We're doing this on screen, poking around with notes paper and pen and pencil. We're not doing this for real. Now, I'm going to be doing this based on what you find in the industry. Let's move on. SAMI specifications for testing 12 gauge rounds is a 30-inch long shotgun barrel. Take it for what it is. Now, we're going to base this on them doing their PSI, or pounds per square inch, pressure limit testing for modern barrels and making them compliant with older barrels by kind of fudging the numbers so we can get away with not killing anybody when they're trying to shoot a goose. The longer barrel has positive and negative effects, but that's the one they use. Black powder, 80 grains in that barrel, firing an average test load, they didn't specify which one, got a 1,500 pounds per square inch, no, a 15,000 pounds per square inch pulse for 1 millisecond. It's a lot of pressure. But after that, it trails off. And again, it's supposed to come up and then trail off smoothly. If you do 82 grains of propellant instead, that's exactly 3 drams. And you'll see that on boxes of shotgun shells, 3 dram equivalent. But when they were really 3 dram or 82 grains of gunpowder, black powder, that would be used to drive 1 1/8 ounce of shot or slug or whatever. Birdshot, buckshot, didn't matter. That works out to that amount of 492 grains of shot. We're going to use grains as a conversion factor here, which is a bad idea, but we have to do it. Now, it would come out at 1,250 feet per second approximately. There's an exact number for tests, but that was average. Again, black powder is forgiving. It gets a really generic set of numbers. There's a lot of variation, but when you do the averages, you get pretty damn reliable numbers. Now, that works out to 1,700 foot-pounds, 1,700 foot-pounds of energy, which is a lot. 50 foot-pounds is enough to kill a person. I think it's like 100 to 200 foot-pounds for a projectile is required to take down a deer. Don't quote me on that. That's not accurate, by the way, but let's move on. Now, that's like if you had 12 pellets in the cartridge, each of them 80 grains. By doing the math, I hope I got it right this time. I fucked up a couple of times. That works out to 142 foot-pounds for an 80-grain projectile out of a shotgun. That's also 6 grains of black powder propelling it. These numbers are going to be important soon. Now, if we did it as 16 pellets, smaller size, not necessarily big buckshot, at 30 grains each pellet, that would work out to 106 foot-pounds each and only require 5 grains of powder per pellet. Now, you notice these numbers aren't really looking exactly like they should? Okay, now I could have been making a math mistake. You're invited to find that. I'm pretty sure I did. But how many foot-pounds of energy do you get out of black powder per grain? Well, it looks like 5 grains of black powder is required to get it to 106 foot-pounds. So that should be 21 foot-pounds per grain. Okay, let's make a note of 20 foot-pounds per grain. But if we do the 142, it's bigger. So let's say 25 foot-pounds per grain. Let's use that as a number for right now. But that's in a shotgun barrel, firing lots of pellets with the propellant pushing all of them and trying to keep them organized like herding cats. Okay, now let's move on. Smokeless powder. If you get enough smokeless powder into the same shell, everything is the same except the smokeless powder is used. And it's presumed it's going to require less because smokeless powder burns almost totally into a gas. Black powder, when it burns, produces waste material. Over half of it doesn't burn. So it just remains soot and sticky stuff. Now, if you're not aware of it, if something can be converted from a solid to a gas, not a liquid, it expands usually 1,000 times over in volume. What that means is it becomes 10 times as wide, tall, and deep. Because 10 times 10 is 100, times 10 is 1,000. So a 1-inch cube of, let's say, smokeless powder in a big cannon that's throwing a bowling ball will expand to a 10-inch by 10-inch by 10-inch cube of gas. And that's before it's even accounting for the heat. There's thermal energy added to it to make that expand very easily, which means you have calorie calculations coming up. Anyway, if you got a 3-dram equivalent per your propellant in your cartridge, everything's the same, but you're using smokeless powder, how much would it be? The one you see very commonly is anywhere from, this is not a joke, 13 grains instead of 82, all the way up to 33 grains. It's depending on the efficiency of it or how fast the curve works or whatever mumbo jumbo. It's the formulations. There's a lot of variation to it. But the largest number of them work out to 18 grains. 18 grains instead of 82. 1/4 or 1/5 the amount needed. Okay. So let's say we're trying to fire a projectile that's 30 grains. And instead of 5 grains of black powder, we need 1 grain. And if we need to fire a 40-grain item, that's a little over 1 grain of propellant if we're using smokeless powder. That's an assumption right there. But would it have 142 foot-pounds or 106 foot-pounds per projectile? Okay, we're going to use something we can do here. Now remember, again, we're talking about the smokeless powder having what looks like 94 foot-pounds per grain. That doesn't match what we just got. But it's kind of close. Okay, let's go. 22 long, not 22 long rifle, 22 long cartridge. They had a short and long cartridge, then they had a long rifle cartridge, and they had another one. That fires a 29 or 30 grain bullet. Let's use the 29 grain bullet that was used in 1871. It came out at 1,038 feet per second, and that was propelled by 5 grains of black powder. Sounds familiar. And it had 62 foot-pounds of energy. That's a lot lower than we should be seeing here, right? I mean, they're doing 5 grains and getting 142 or 103 or 106 or whatever out of a shotgun shell. Okay, let's move on. The 22 caliber short, which is a shorter casing with 4 grains of propellant, not much of a change. Firing a 30 grain bullet exactly. 1857 was able to get it up to 1,132 feet per second for 82 foot-pounds of energy for that one pellet at 30 grains. Now again, up here, if we did 30 grain, 16 pellet, 12 gauge shell, we got 106 foot-pounds out of 5 grains of propellant. Well, it's a different volume. It's pushing behind a very tight seal of one pellet, a bullet. The buckshot or birdshot or whatever you want to call it coming out of the shell is being pushed by a shot cup that's trying to do all the work for it. That means it's spreading it out over a larger area than if they were all in a straight line or if they were all tightly packed in some optimized way. It's a different bore. A 12 gauge, if you're not aware of it, is just slightly less than a 73 caliber firearm. Okay, let's try 22 long rifle. It has a 40 grain bullet in this time. 2018 timing, we're using smokeless powder. 1,200 feet per second, really close to what we get out of the shotgun at 1250. And it has 120 foot-pounds of energy, and it was propelled by a single grain of propellant, smokeless powder. That's a 40 grain bullet at 120 foot-pounds of energy. Now again, when we look up here, we get 142 foot-pounds for a 40 grain 12 pellet shot, each one of them done by 6 grains of propellant. So that's a 1-to-6 ratio. Now we had a 1-to-4 or 1-to-5 ratio if we just did the 12 gauge and did apples to apples. But if we do it when we base it on a 22 caliber bullet out of a 22 long rifle with a lot of dead space in it, gunpowder doesn't like dead space, but it creates a snappy spike, which means it works really good in short barrels. But you have to over-design the hell out of it, so make a really thick barrel and put a little dinky bullet in it. 22. Now, let's look at black powder measurement, experimental for firing cannon. 150 grains of black powder was measured as being able to, under optimal conditions, by math and also by practice, get upwards of 20,000 foot-pounds of energy out of the muzzle from, I don't know what was shot out of it. It could have been a beer can. It could have been, a dead pig. Don't matter. Then that should work out to 135.75 foot-pounds per grain as a rule or as a maximum. This was an experiment that was done by people doing real chemical experiments with, honest to God, black powder. Now, again, per grain, it was 135 foot-pounds. That's bordering on what we're talking, but wait a minute, those was 6 grain for the shotgun. But per grain, per powder, yeah, we're not getting that here. Well, again, that was an optimized, they picked a certain bore, they picked a certain weight. If you put too little weight in front of the propellant or too much, it's not going to be able to transfer the energy correctly because it's not balanced for it. That's a whole other universe of stuff, but basically look up impedance matching in the world of electronics and radio signals and get the idea. If you don't match what you're shooting with what you're propelling, it doesn't work. You can see this in bow and arrows. You put a certain weight of arrow on a certain pounds of bow, it works great. But if it's too light or too heavy, it wastes the energy. It wastes the energy trying to get it moving at all, or wastes the energy throwing it before it's put all the energy into the bolt, or the arrow as it's called. It's called a bolt. So let's look at theoretical maximums. Here we go. If black powder, by definition, has just calorie energy, 678 calories per gram. We're using grams now for your European people. And if a gram is 15.4 something grains, then black powder has a hypothetical 43 or 44 calories per grain value. Now you can take the total calories and multiply that by 3.09, that's the equation, to get foot-pounds. Then that means black powder per grain maximum hypothetical is supposed to be 135.75 foot-pounds per grain. And that actually works out in a lot of this or all of it, depending on what you're doing. Again, the optimization, the balancing, whatever. That's why it's an art more than a science. That's why you read the instructions on the powder that you buy. Otherwise, it'll blow up or it won't even work. Byproducts from black powder make it less efficient, but make it more forgiving on the spikes. Smokeless powder, a lot more energy potential for the same volume. And you can base it on the caloric energy, the heat, as well as the expansion ratio and how efficient it is. And if you don't learn enough about this, you'll be the victim of your own stupidity, or worse, someone else downrange a mile away. Thanks for watching. Have a good day. Good luck with that. Further links below in the description if you want to look up the theory.